Hello everyone, myself Sindhuja. I'm from branch EC and my roll number is that 23401A0487, and today's my topic is on wave propagation in good conductors, and I took this from electromagnetic waves and transmission lines, and the subject code is that 23ECE401. Let us know what is mean by wave propagation and how does it works. uh, Let us know about what is wave propagation, how does it works as good conductors, what are applications of the wave propagations. When it comes to what is mean by wave propagation, let us know that wave propagation refers to the movement of waves through a medium or space. It describes how disturbances such as electromagnetic waves, sound, or water waves travel from one point to another. The process depends on the type of wave and the properties of the medium through which it moves. As shown in the figure, we can observe that how the wave propagates through the propagation direction. And when it comes to wave propagation in good conductors is characterized by large attenuation or loss of amplitude as the wave moves through the conductor. The wave's amplitude decreases to almost zero within a few skin depths. Let us know basic definitions through the wave propagations, explanation about the skin depth and what it does mean. A measure of how far an electromagnetic wave can penetrate in a conductor. The skin depth decreases as the wave frequency increases. When it comes to attenuation, the amplitude of the wave decreases. It moves through conductor. The phase velocity of a wave in good conductor increases the frequency and decreases with conductivity. Let us know what is mean by reflection. A perfect conductor reflects wave with a 180 degrees phase change at the interface. Absorption, some of the wave energy is absorbed by the conductor, which corresponds to the energy lost due to Joule heating. Wave propagation in good conductors acts as four types. Conductivity sigma equals to 0. Permeability mu is equals to mu naught into mu r. Permittivity epsilon equals to epsilon naught into epsilon or sigma less than equals to omega e by sigma less than 1. In good conductors, we have propagation constant. The propagation constant describes how a wave propagates through a medium. It is a complex quantity that describes both attenuation and phase shift as the wave travels. Gamma square is equals to j omega mu into sigma plus j omega epsilon. Uh, Gamma is equals to root of j omega mu minus 1 plus j omega epsilon by sigma. Gamma is equals to root of j omega epsilon. Finally, we got that gamma is equals to alpha plus j beta. When it comes to second one, that is attenuation constant, it is represented by alpha, and it is a measure of how much a wave, such an electromagnetic or sound wave, loses amplitude as it propagates through a medium, and it is expressed in efforts per unit or decibels per meter, dB by m. Attenuation constant alpha is equals to omega w root of mu epsilon divided by 2 root 1 plus sigma plus w epsilon whole square minus 1. C is equals to root of w whole square root of mu epsilon by 2 into sigma by w epsilon whole square. Sigma by w epsilon becomes less than greater than 1. Then finally attenuation constant alpha, we got that root of w mu sigma by 2. When it comes to third one, that is phase constant, it is represented by beta. It is a measure of phase shift per unit length in a wave as it propagates through a medium. It is expressed in radians per meter and is a key parameter in wave propagation, transmission lines and optics. Beta is equals to W root of mu epsilon root of 1 plus sigma divided by W epsilon minus 1. We got that beta is equals to root of omega epsilon sigma by 2. Therefore, alpha and beta, whereas attenuation constant and phase cost constant, we got the same root of omega mu sigma by 2. When it comes to fourth one, phase velocity, it is represented by v suffix p. The phase velocity is speed at which the phase of a wave propagates through space. Vp is equals to omega by beta. We know that beta is equals to root of omega mu sigma by 2. Vp is equals to, substitute beta in above formula. Vp is equals to omega by root of omega mu sigma by 2. We got phase velocity is equals to root of 2 omega divided by mu sigma. When it comes to fifth one, intrinsic impedance, it is denoted by neta. Intrinsic impedance is a fundamental property of a medium that describes the relation between the electric field and magnetic field in electromagnetic wave propagating through the medium. Neta is equals to root of j omega mu divided by sigma plus j omega epsilon. Neta is equals to root of j omega epsilon by j omega mu by j omega epsilon into sigma divided by j omega epsilon plus 1, whereas sigma greater than omega epsilon and sigma by omega epsilon greater than 1. Finally, we got that intrinsic impedance is equals to root of j omega mu divided by epsilon. And applications of the wave propagation, communication system like radio, TV, broadcasting, mobile network and Wi-Fi, etc. Medical applications like ultrasound imaging, MRI. MRI is nothing but magnetic resonance imaging and laser surgery, etc. Industrial and engineering applications like seismic wave analysis, microwave heating, etc. Space and astronomy like radio astronomy, gravitation wave detection and satellite communication. Finally, the conclusion of wave propagation is that it is the movement of waves through a medium or space, transferring energy and information. It occurs in different forms, including electromagnetic waves such as light, radio waves, mechanical waves like sound, water waves, and matter waves in quantum mechanics. When it comes to the key properties of the wave propagation, including that wavelength, frequency, phase velocity and the group velocity, which determines how waves travel and how they interact with the surroundings, and it can refract and experience absorption or attenuation based on medium as they pass through. The nature of medium, whether lossless, lossy, dispersive or non-dispersive, affects behavior. It is the fundamental to various applications including the telecommunications like radio, optical fibers, medical imaging like ultrasound and MRI, industrial and defense technologies like radar, sonar, and scientific research, radio astronomy, gravitational waves. By understanding the wave propagation is essential for advancing technology and improving the communication, navigation, and diagnostic system. Thank you.